All right, so our definite integrals allow us to solve problems involving the accumulation of change over an interval. Okay, that means we're going from A to B or something. That's your definite integral. A function defined as an integral represents an accumulation of a rate of change. Okay, it's an accumulation of a rate of change. The definite integral of the rate of change of a quantity over an interval gives you the net change of the quantity over that interval. Okay, so if it's a function defined as an integral, represents an accumulation of the rate of change. The definite integral of the rate of change, so basically like when we did velocity, the definite integral of the rate of change of like velocity, then that gave us the net change of the distance that we were looking for. That's what that's saying, basically, just in more generic terms. So let's look at what this says for us. It says the rate, we have a rate at which rainwater flows into the drain pipe is modeled by the function r, where this is our function, cubic feet per hour. Okay, so this is feet cubed per hour. T is measured in hours. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So right now we are doing integrals. So obviously we're going to take an integral. But when you need to decide, am I supposed to take the derivative here or am I supposed to take the integral, the units can tell you a whole lot of things. If we just think in general terms, we'll use feet and hours just like we have here. I start off with, so like my function would be in feet, right? My derivative is a rate. That's when it would become feet per hour, right? And then my f double prime would be feet per hour, right? So if I have feet cubed per hour, not just feet, but it's feet cubed, but that part doesn't really matter, and I want how many cubic feet, that means here I am, I want this, so I have to go backwards, which means that's an integral. Where if they gave me feet and I wanted the rate, that's how I know it's a derivative. Does that make sense? You look at the units and that can tell you which way to go. All right, so we are going to take the integral. We want the integral of r of t. And here's the thing. On the exam, I could write the integral of r of t, or I could write the integral of this right here. Either one is fine. But if it's already defined as this, you can write that so you don't have a copy error. Because this is a calculator question. I know it doesn't say it, and on the real test it does say that. So it's not like I'm going to have to do it by hand. Okay, it's a calculator question. So r of t dt, I have an integral, so I have to have that. And I'm going from 0 to 8. Okay, everybody okay with that? All right, so and here's what we have. This right here, that r of t, that is cubic feet per hour. This is the change in time, which is hours, and they're being multiplied, and that's why then these cancel out and you get your feet cubed when you do the integral. That's what's happening, okay? All right, so we're going to go do this on our calculator. So I'm going to add, and remember, I could just type this in, but most of the time you're going to want it in the graph just because there's more things you might do with it depending on the question, if it was a different question. And then we're going to type this in, 20 times the sine of x squared over 35. I opened parentheses and they were already opened. Not necessary, but I also don't have to fix it as long as I close them both, and then I'm good. That's what mine looks like. Is that what yours looks like? Yep, looks like a parabola. Is it a parabola? No, it's not. You can kind of see that there's more out here. It's clear. Whoops, it's really not a parabola. Okay, but it doesn't matter because we don't have to go by that way it looks. So I'm going to control, I'm going to add a page, I'm going to add a calculator. and I want to do the integral. And y'all told me you liked the little button better than the menu, which is fine. So this little button next to 9, it's probably because y'all have better eyes than I do. And then this little thing here, we're going from 0 to 8. And what do I type here? f1 of x, and then I got to make sure it's dx. I feel like putting it in the graph, even if I only have to do one thing with it, still it's better than having to type it here. But again, it would actually work either way, and that's what we get. Okay. All right. So that means my answer is 75.570. 570, and then I need my units in there. What did I say? What did I do? Oh, it is 76. Good Lord. 76. Can't even write numbers down correctly. All right, how are we doing? We good? Okay. All right. So the rate at which water enters a tank, is this. And this is gallons per hour. To the nearest gallon, how many gallons of water enter the tank during this interval here? Okay. So this is another calculator question. I'll tell you that from the beginning, because then that can change how you write out what we're going to write out. I have gallons per hour. I want gallons. I'm going backwards, which means I'm integrating. So I'm going to integrate from 0 to 7, and I can write f of t dt. But you cannot forget the dt, and you can't use x when it says t. Like, you have to be accurate about those things. And again, this is gallons per hour times hours. That's why it's going to get you your gallons. But we can go back to the calculator. Really, the best thing to do is just hit on and get a new one every time. That way you don't have to worry about anything being saved weird or whatever. I'm going to add a graph. You go ahead and do the rest. There's my graph. That's what I got. Everybody good with pushing the buttons? Okay, so this gives me 8,263.806 gallons, which is really 8,264 gallons, because it did ask for it to the nearest gallon. Okay. Now, we're going to do something on the calculator. So most of the time we don't save documents, right? But I feel like so when you're doing the AP test, you're going to have FRQ1 and 2 that are both calculator. And if you do something on FRQ1, you create a new document, you're in FRQ2, and you're like, dang it, I know what to do in FRQ1. Well, you don't want to have to go back and type in everything, right? So I'm going to show you how to save documents. Right now we'll use them, we'll save them as like example 1 and example 2, but you could literally name it FRQ1 and FRQ2. So when you're here on your calculator, okay, and we can just click the on button again, And when you go to new one, and it says, do you want to save, quote, unsaved document? We're going to say yes. Okay? And then it lets you put a file name. And so on the test, I would probably put FRQ1, but we'll just do like example1, if I can't, example1, something like that. And then we're going to save. Okay? And then it looks like it went away. But that's okay. Because now, let's go ahead and we're going to do this next one, and then we're going to come back and look at what we had. Okay? Does that make sense? So you can figure out how to get back to it. So you're here. Now we're going to add another graph. Okay? And then we're getting ahead of ourselves because I wanted you to save that. Let's see what we need to put in here and what's happening here. At an intersection in Thomasville, Oregon, cars turn left at this rate of cars per hour over this time interval. To the nearest whole number, find the total number of cars turning left at the intersection over this time interval. So I want you to write everything that needs to be written and type in everything that needs to be typed. I'm just going to let you kind of like do this whole thing on your own to make sure we can also write down what needs to be there. Mm-hmm. Oh my goodness. I really have no idea. Sometimes if you get sliders on there, I would just hit on and start over. Or just leave it either way. Like, does it bother you?
No, I'm just trying to
Oh, maybe you did. Oh, yeah, sorry. Got to start over anyway. Sorry about that. Okay. All right. So let me see what you got. Okay. Okay, so that's part of the problem, okay, and that's why I wanted you to do this one, is you can't put exactly what's on the paper. Remember that, remember how if we were going to integrate or even take the derivative ourselves, how we would rewrite that? What you want to type into the calculator, you're going to type in, well, you're not typing in L of t, of course, but you're going to type in 60 square root of t sine of t or x, I'm sorry, I'm putting t's, and then squared like that. That's what the calculator is going to understand. So basically you have to write it like you would rewrite. Don't roll your eyes at me. I didn't make these calculators. But do you understand what to do there? And the good news is you can't really do it wrong because it tells you it's not even going to take it. It's not going to give you like something different and weird.
It automatically fixed it for me.
It did automatically fix it for you? Did it fix it? You know what you might have done differently than them is do you put them times right here?
No, I just put square root of x, and then I got out of the square root.
Yeah.
And then I put sine, and then I tried to square it, and I just took it in parentheses, put the square root on one side of the parentheses.
Okay, so I wonder what they did differently and what I've done differently in the past. Okay, well, let's try that. I'm just going to do sine. I'm not even going to, well, maybe I'll just do the whole thing. Never mind. 60 times the square root of x, right? Okay, then we get out of it. And you just did sine and did squared?
Yeah.
Sorry, I'm still semi-learning these. But where'd you?
The square root.
Like, so did you arrow, like, how did you get a square on the sine, though?
Press square root.
Like that? Okay, come. Oh, wait. Oh, that's what you can do. Okay, I bet you that works. Let's see if this works. So when you're here, I tried to arrow. If you delete it, let's see if this works. Oh, no. This stupid board. 60. Okay, let me square root of x. Okay, so then I'm going to do sine, and then I'm just going to hit delete once. Okay. Y'all saw me do that, right? Okay. Well, maybe y'all can try this. It doesn't work either? Yeah. I don't know if you got lucky because I don't. Yeah, I don't. There probably is a way. Let me put it that way. There probably is a way. He got lucky. If you can make it work. Does your graph look the same as ours? Let me see what you have. Oh, but yours looks like the way it's typed in is what I typed in. See, it doesn't say sine squared.
Yeah, because if you get out of the parentheses, you don't need.
Oh, I think I know what you're saying. Did you do it like this? So like if I do sine, if I do it over here and then square it, oh, no, it won't even let me do that. Yeah, I don't know what you did. I don't know what you did, but if you ever figure it out, let us know. Otherwise, we're going to continue to do it this way. So basically, his ended up looking exactly like ours. He just magically did something else. Or maybe he didn't. He thinks he did. I'm sure he did, but nobody else could get anything else to work, right? Okay, I didn't think it did, but I'm not going to say that I know everything about this. Okay, but we got that at least? All right, so go ahead and finish the question if you haven't. And then, so this is not actually this is for the calculator. It's not actually you don't actually have to write that down. But here's what you do have to write down. We're going to integrate from 0 to 18 of L of t dt. Again, you could write this instead of L of t, but if you have a copy error there, that's real bad for you. And don't forget your dt. Then you just get this out of the calculator. We got 1657.823. It does say the total number of cars to the nearest whole number. Now, here's where there can be an argument. You can't have, how many people fit on a school bus, right? If it's 43.5, you can't round that up to 44 because that other half a person's not going to fit, right? So whether or not you round this up or not, you could have an argument about it, but rounding says most of the time they're not going to ask you to round. Oh my God. Most of the time they're not going to ask you to round this stuff anyway, and they're not going to be crazy about it. But it's a good idea to just go ahead and write that down, so that you have it and then go with it. All right? What questions you got? We good on those? Yes? Okay, so now in our calculator, we're going to save this. Ready? We hit the on button. Let's just hit new. It's just the easiest way to do it. Then say yes. We're going to name this example 2, so just EX2 or whatever you want to name it. I don't care. And we hit enter. Okay? Now, so we just worked on FRQ2. Now we're like, oh, I know what I can do on FRQ1. I want to go back to it. So we hit on. And you see how you have new, browse, recent, blah, blah, blah. So it really should be in your, you can either do browse or recent. Either one, but if I browse, it's going to show me everything. I probably have more stuff than you do because I automatically have all these folders. But there's your example 1 and example 2. So if you click on, you highlight that and click on example 1, then we are back to example 1, and you have all of your pages that you had there for that one. Okay, and so that way you can save them and you can go back and forth if you need to. Or you can always just retype everything in, but sometimes it takes a minute to type this stuff in and it can get frustrating, right? What questions you got? We good? Beautiful. Okay. So enough. So now let's just get another new one and just leave it at that for just a second. All right. Here we are. So we're looking at T cooling here. I have mine are in different orders here. Okay, and we do not actually need our calculator for this right now. All right, so as a pot of tea cools, the temperature of the tea is modeled by a differentiable function, H, where time t is measured in minutes. So t is in minutes, temperature is in degrees Celsius, values of h of t at selected values of the time are shown in the table above. Okay, use the data in the table to estimate h prime of 3.5. We are estimating an instantaneous rate of change, which means we can't find the instantaneous rate of change because we can't actually take the derivative, but the rate, this is the rate of change of this right here. So basically it's just asking you for basic slope, right? So what we want here is we want to write h prime of 3.5 is approximately, right, because we're estimating. And then 3.5, well, that would be in here. So really you could estimate it a lot of ways, but the best way is to estimate it with these two, right? So I would say h of 5 minus h of 2 over 5 minus 2. And 5 minus 2 is 3, and we all know that, and it's easy. Do not, well, we hope we do, but we do not write 3 there, you write 5 minus 2. One of the things that they are looking for is a difference quotient where you literally subtract things, okay? So it may seem ridiculous, but that needs to be there. All right, so then h of 5 is 52 minus h of 2, which is 60, over, and I could leave it 5 minus 2, or I could put 3 here. It doesn't matter either way. Do I have to actually go any farther at all? No. Okay, so this is fine. And then we can interpret, so it says using the correct units, interpret the meaning, okay? So we can say the temperature of the T, the temp of the T. Now, just by looking at that, and we haven't done anything else yet, is that answer going to be positive or negative? Negative, okay? And that is so easy. Maybe it would be easier for us to actually finish it. Like, it's up to you, right? What you want to do either way. But you're either going to have to rewrite that stuff and figure it out, or, you know, or either rewrite it, and if it's a hot mess, whatever, you could write it like that. Is it increasing or decreasing, I guess is what I'm trying to say. Decreasing, right? Because it's cooling. I mean, they said it that, right? Plus, it's negative. So let's just go ahead and write that. Might make it easier for us. But again, you totally don't have to, okay? The temp of the T is decreasing, yes? Decreasing. Yes, because actually going down, that kind of could mean a few different things, and so we decreasing. Plus, look, you've got just DEC, it's just decreasing, just make it easier, right? Okay, decreasing at, do we know an exact rate? No, approximate rate. And then at an approx, you can abbreviate, rate of 8/3 degrees Celsius per minute at t equals 3.5 minutes. And instead of writing this, you could write this. That's totally fine as well, either way. But notice, this is what I want to make sure you notice. I got a negative 8.3. Did I put a negative 8.3 right here? No, because I put decreasing, right? So that's, and you need to say if it's increasing or decreasing. You can't just leave it. You have to be very specific about these things. Okay? What questions you got? All right, good deal. So then, using the correct units, we're going to explain this meaning in the context of this problem. Use the trapezoidal sum with 4 subintervals. We're actually, just for the interest of time, we are just going to explain it and not do the actual trapezoids because those take a minute, and I want to get to some other ones here. Because I want to make sure you understand what these mean. Okay? If I'm going from 0 to 10 and I'm multiplying by that 1/10, that's going to be an average one, right? And it's always the average of whatever this is. So like if I integrate velocity, I get position, right? But if I integrate velocity and multiply it by that 1/10 or whatever on the outside, I'm getting average velocity. So it matches whatever this is. Okay? So what does h of t represent? Look at the paper, don't stare at me. Degrees Celsius. Okay, thank you. Goodness gracious, guys. All right. So 1/10 times the integral from 0 to 10, because this is my b minus a right here, right? Of h of t dt is the average, okay? So average because of this. It's the average, whatever this is, which represents the temperature of the T in degrees Celsius from T equals 0 to T equals 10. What are the units? Minutes? Minutes. Okay. All right, so now on C it says to find this and then interpret it. We're just going to interpret it, like I said, because I want to get to that other page. I just have the integral of h prime of t. Is this an average anything? No. If I integrate the derivative, I get the original, right? So if I have h prime of t and I integrate that, that's going to give me h of t. But it gives me this gives me an accumulation of h of t. Does that make sense? It's not just h of t. Okay, so what this means from 0 to 10, h prime of t dt is the total change in temperature from t equals 0 to t equals 10 minutes. Ooh. All right, what questions we got? We good? You understand how those work? Okay, because it doesn't do you any good if you can find all this stuff, but you don't know what the heck it means. All right, so let me give you your second piece of paper so we can get through at least one or two of these. Figure out which ones I want to do. Okay, so I don't think we have time to do all of them. I know that breaks your heart, but let me see which ones I think I want to do. Yeah, I want to do this one for sure. Okay. We'll just start at the top and see what we can get done, because I want to do that one. All right, so we have a cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when t equals 0. The coffee's temperature is changing at this rate, okay? Degrees Celsius per minute with t in minutes. I want to find the coffee's temperature when t equals 10, okay? If I'm going to integrate, that gives me an accumulation. This is not asking me how much it changed in those minutes. It is asking me what is the temperature right then. That is different, okay? It is asking me for a final temperature at 10. This is where that fundamental theorem of calculus comes in, okay, where we could set it up two different ways. I could set it up as, well, I know that the integral from, let's see, I'm starting at t equals 0, from 0 to 10 of r of t dt would be equal to, now, if I integrate little r, what do I get? Big R, right? This would give me r of 10 minus r of 0, right? That is your fundamental theorem of calculus. I am looking for r of 10, right? So I'm going to add this to both sides. So big R of 0 plus the integral from 0 to 10 of r of t dt equals r of 10. Now, you don't have to write this first, but you do have to recognize that it's the fundamental theorem of calculus. If I want the temperature when it's 10 degrees, I'm going to take the temperature at 0 degrees and add however much it changed. Does that make sense? That's what's happening. And if you can reason through it and just write this directly, that's totally fine. Sometimes it's addition, sometimes it's subtraction type of thing. All right, do we know r of 0? 90 or 20? Which one? The cup of coffee is 90 degrees Celsius when t equals 0. So they put both of those in there, make sure you're paying attention. So r of 0 is equal to 90. Okay? So that means I get 90 plus the integral from 0 to 10 of r of t, that looks like a 16, r of t dt. That's going to equal r of 10, which is what I want. So I'm going to go to my calculator, and I'm going to go to my graph. I'm going to add a graph, and I'm going to type in that equation. I lost my piece of paper. Crap. Did I? Oh, it's right here. All right, so that's, when you're using the negative sign, make sure you use the one next to enter. Don't use the minus sign. Negative 7e to the negative 0.1x, I think. So that's what we get. Yep. Then I'm going to add a calculator. And on my paper, I have 90 plus, so 90 plus, get my integral. I'm going from 0 to 10. f1 of x dx. Okay, everybody okay with that? And see, I am going to need to use that function again, so it's good that it was typed in the graph, because then I don't have to retype things. All right, so my answer then is, so r of 10, and it doesn't say I have to explain anything, is 45.751. What are my units? Degrees Celsius? Okay. All right. So this says find the average rate of change of the temperature of the coffee over the first 10 minutes. This is the rate of change, right? If I want the, so the rate of change over the first 10 minutes, so r of t dt, right? If I want the average of what's in here, this is 1 over 10 minus 0. Does that make sense? I found the average of whatever this is. Okay, that way you're not overthinking which way we're going or whatever. That's the way the average parts of these work. So back in the calculator here, I can start with 1/10. Maybe if I can actually get in my fraction. There you go. 1/10. And then I'm going to get my little thing here. Oh, not what I wanted, right? Oh, my Lord, have mercy. Okay, times 0 to 10 f1 of x dx. All right, so does that make sense? Yes? Okay. And so that gives me negative 4.424. And what are my units on here? Degrees Celsius, good, per minute. When we integrated r of t dt, we got degrees Celsius. Oh, and then we multiply or divide it by minutes, so that's where your degrees Celsius per minute comes from there. Okay? We good with that? What questions you got? All right. Y'all doing okay with the calculator? Yes? No? Maybe? Okay. This says water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at this rate. At time t equals 0, the tank contains 30 gallons of water. How many gallons leak out of the tank from 0 to 3? So how many gallons leak out? It says that water's being pumped in, but this A part doesn't ask me for that, right? It asks me for how many gallons leak out. This is the rate at which it leaks out. Yes? Okay with that? So I want to integrate that. If I integrate the rate, I get how much, right? If I integrate gallons per minute, I get gallons. So from 0 to 3, and that's the square root of t plus 1 dt. Can you integrate that by hand? Yes, we can, right? So I could rewrite it as the integral from 0 to 3 of t plus 1 to the 1/2 power dt, yes? So when I integrate it, I get, do I really have to use u substitution here? No. And if you understand u substitution, you can understand that you don't have to here because it's just t plus 1, and I would just get du, and we're fine, right? All right, so I'm going to add 1 to the exponent, right? So this actually gives me t plus 1 to the what power? 3/2. And then I divide by 3/2, which is the same as multiplying by 2/3, right? And then I'm going to evaluate it from 0 to 3. Okay, everybody good with that so far? So let's substitute in the 3. I'm just going to write down the 2/3 here. Let's think about what this thing means. So 3 plus 1 is 4. Which one would be easier to do first, the 3 or the 1/2 part? The 1/2. Doesn't this mean I'm going to take the square root and then cube it? Or I can cube it and then take the square root, but I think it's easier to do it the other way. So 4, I take the square root and get 2, and then 2 cubed is what? 8, okay? Then plus, nope, not plus, minus, because that's the way you do it. Minus, that looks like a minus. I substitute in my 0, I get 1. Well, 1 to the 3/2 power is 1, so it's just minus 2/3. Okay? I have 2/3 times 8, so this is going to give me what, 16/3 minus 2/3, which gives me 14/3. And what are my units on there? Gallons. Just gallons. We're just going to set this part up. How many gallons are in there at t equals 3? Not how much is leaking out, whatever. If I want to know how much is in the time at t equals 3, then I want the initial amount. How much is in there initially? 30, right? And then I'm going to have to subtract from that how much has leaked out, right? Which is this integral that we just found, 14/3. Am I going to have to add anything to it? water's being pumped in, right? Plus the water that's being pumped in, 8 gallons per minute, so that would be 8 times what? 3. And then that would give it to you. Okay? All right, we good? All right, good deal.